Hey, I'm Kok Jin Shen. Do you know how camera flash works? Do you know how AED flash works? If you have no idea about it, you are at the right place. Let me introduce you the capacitance. Let's start with the capacitor. So, what is a capacitor? Capacitor is a device for storing electrical energy consisting of two conductors in close proximity and insulated from each other. Where can we find a capacitor in our life? This is a very standard everyday digital camera, and if you open the cover of the camera, you will notice something that looks kinda like a battery. So this big cylinder here is specifically for the flash. In a digital camera, we will have a built-in flash capacitor and batteries to charge the capacitor for the flash. When you are using the flash, obviously, a lot of energy in that burst of light will be discharged. If you have taken a lot of flash photographies, you will notice it takes time for the flash to recharge for the next photo. You can't snap pictures continually with the flash because there is some delay for the capacitor to build up the energy. In a capacitor, there's two plates that kept side by side in a small distance. The space between the plates usually is vacuum, but sometimes it may get filled with dielectric. The gap between the capacitor does not allow the charge to pass through it. The conducting wire connected to the positive terminal of the battery is at higher potential, and the one connected to the negative terminal of the battery is at lower potential. This constant potential difference induced in the circuit due to the battery drives free charges that is present in the circuit. A metal typically has equal amount of positively and negatively charged particles, making the metal as a whole electrically neutral. Let's say if we only have one side of the plates. If we apply a force trying to push extra electrons into the middle plate, we will not be successful, because the particles with the same charge repel one another. If extra electrons accumulate inside the metal plate, they will repel each other and repel any new electrons trying to enter. Therefore, even we have applied a force, the metal will remain electrically neutral. Now, let us consider a new scenario where is another metal plate close to the one shown. As electrons accumulate in the first metal plate, they will repel the electrons in the second metal plate. The positive charged particles left behind in the second plate will exert an attractive force on the negatively charged particles in the first metal plate. This makes it possible for the first plate to have more negative particles than the positive particles. The first metal plate has developed a net negative charge, and the second metal plate has developed an equal and opposite net positive charge. Now, suppose we increase the areas of the two metal plates. This increased area allows us to push more extra electrons into the first metal plate and remove more electrons from the second metal plate without applying a large external force. In other words, by increasing area of the metal plates, we can increase the capacitance of the capacitor. Besides that, this is the two metal plates closer together. Because the two plates now closer together, they exert greater forces on each other's electrons. This attracts more electrons to the negative plate and repels more electrons from the positive plate, allowing the two plates to develop larger net charges for the same amount of applied voltage. This can also increase the capacitance of the capacitor. Suppose that we add a special material called dielectric in between the two plates. This material does not allow any particles to flow through it, but it contains molecules that can change their orientation based on the charges of the two plates. Molecules exert forces that attract more electrons to the negative plate and that repel electrons from the positive plate. The presence of this material can increase the capacitance of the capacitor as well. As a conclusion, to create the largest capacitance possible, we want to make the area of the plates as large as possible. Insert a dielectric between the plates and also move the two plates as close together as possible. Now, let's try to calculate the capacitance of a capacitor. After the capacitor has been charged, the potential difference between the plates becomes equal to the potential difference of the batteries. Let positive Q and negative Q be the charges of the potential difference V. Charge density of the positive plate. positive sigma is equals to positive Q by A. And then on the negative plate, negative sigma equals to negative Q by A. From the previous topic that we have learned, the uniform field between the plates equals to sigma by epsilon naught. So, the electric field is Q by epsilon naught A. If the distance between the plates is D, the potential difference between the plates V is equals to E times D. Substitute E to Q by epsilon naught A. Q by V equals to epsilon naught A by D. Q by V is nothing but the capacitance of the parallel plate capacitor. Hence, the capacitance of the parallel plate capacitor is epsilon naught A by D. For additional information, in series circuits, the reciprocal of equivalent capacitance is equals to 1 by C1 plus 1 by C2 plus 1 by C3 and so on. For parallel circuits, the equivalent capacitance is just equals to the sum of the capacitance of the capacitors in the circuit. That's all for this video. Thanks for watching.